Hello and welcome back to Calculus 1. It's glorious Saturday morning, right? Whatever it is. Saturday, it's weekend, you're all happy. Do some math, you love it. So we're going to continue our exploration of limits. The first lecture of today is the techniques of computing limits, meaning algebra. So today we are going to use algebra to solve limits. Last time, when we talked about limits, I said that the limit is technically figuring out the y value of the function. And we've seen the example where the limit of x squared as x goes to 3 was 9. And in some sense, you would like to say, well, all I do is plug x and obtain y. But then we also ran into situations where you cannot do that, because you would get, like the example for homework, you run into a situation where you plug in x values and you get 0 divided by 0. You might also get infinity divided by infinity. You can get all of these different values that you actually can't compute in the end. So the way to solve the limit, you have three main ways to solve the limit. Number one is graph. That was in 2.2. Number two is chart, table of values. Also 2.2. And number three now, algebra, 2.3. So these are the ways to compute the limit. The simplest form to solve the limit is to plug x in. If it works, you get the answer, you're done. So from here, the simplest way is to plug in the x value however, it doesn't work most of the time, right? Example when it works, which was our introductory example to limits, would be this one, right? 3 squared is 9. Now again, this is a wrong way to compute the limit, because remember, limit is not supposed to compute at the point 3. It's supposed to compute around points 3. But no, it's practical shortcut, so why not use it? We can. Hell breaks loose when you run into a question where if you plug in your value, you get 0 over 0. So here, method did not work. Now the sad fact is that you resort to, oh, does not exist, because you got over 0. That's also really bad, because the limit for this particular question is 1. And if you don't believe me, graph it and then use your eyes to see that limit is 1. All right? Or do the chart. We are going to use that powerful method which Bernoulli developed in chapter 4, where you take derivatives, plug values in, and then you get 1. But for now, it's charts and graphs. So method didn't work. We have to use other means. And to get 1. So I'm not solving this problem right now. These are examples that tell you that if you plug x as a value and get the answer, such as 9, you are done. And consider yourself lucky, because few examples will do that, right? That we consider in calculus. Most of the time, when you plug your value x, you will get some form of 0 in denominator. You might get 0 over 0, you might get infinity over infinity, you might get all of these different combinations that we will see later on. And those simply say, plug-in method doesn't work, you have to use something else. What do you use? Well, for now, we are going to use factoring from algebra, rationalizing if it includes square roots, adding fractions, and a whole bunch of other things that are possible that would algebra permit us to use. So let's see a few of these examples. Before we start calculating, sometimes it's necessary for us to split limits into multiple limits. If you remember your logs from PreCalc1, you might remember that logs had those properties where you can break logs apart, put logs together, right, to expand them or to contrast them and so on. So we have rules for limits and derivatives and integrals that do such things. So first we're going to take a look at these limit laws, which will be helpful in certain cases to solve these limits. So limit laws first. Since this is not honors section for the Calculus 1, we will not be proving these, but the proofs for these are very easy, looking at 2.7 later on. All right, so what do we have? Law number 1 is the sum law, which says that limit x goes to a of f of x plus g of x. So if you have two functions adding, it's like x squared plus 3x, okay? So x squared would be the f of x and 3x would be g of x. So if you have something like that, you actually consider each one of these independently. So you can just focus the limit of f of x and then add limit of g of x. The next one is the difference. And it's the same thing, except with the minus sign. You will notice that these rules are the same as rules of combining functions. Remember what limits do. They compute function values. So technically, this is like combining functions. You are not going to have all of these rules available like this for derivatives or integrals, because those are operators. And they work different way. One of my favorite, constant multiple, which technically says kick the constant outside. You can kick the constant in front of the limit and then just consider the function. which is really cool. Product. So this is a dangerous rule, because this rule doesn't work for derivatives and integrals later on. We will have product rule and also for division quotient rule. Those rules work this way only for limits. They do not work for derivatives and integrals. So you'll have to pay attention here. We also have to specify that limit of g of x cannot be 0, because we are not allowed to divide by 0. Rule 6 and 7 are the same rule, but for some reason, author of the book believes that we should write them as 2. So if you raise the function to some power, you can actually take the limit of the function first and raise everything to that power. The last rule is the same thing, except instead of writing n, you write fractional power, which is n over m, which will allow you to take square roots, cube roots, and so on. It requires positive functions because you can't take square root of negative values, right? So that would be the list of all limit laws, limit rules. And these actually are handy for proofs. They're handy for very complicated examples, and some of these laws will transition into derivatives, which would be very important rules for derivatives, and some also integrals, and some will not. As I said, the product and the quotient. So numbers 4 and 5 do not translate. Also 6 and 7. So only the first 3 would be moving on and surviving, and the last 4 would not. All right, so the types of examples that the textbook has for you to practice this are where they ask you for the limit of some kind of combination of functions, where they give you individual answers and you just plug in. So they're very simple. Say you have let limit of f of x be 9, limit as x goes to 4 of g of x to be -3, and limit of age of x as x goes to 4 to be, yeah, whatever, 2. So let's say that's compute age limit as x goes to 4, obviously, of age of x squared minus g of x over f of x. So that would be the question, right? You employ limit laws where you have a limit of a quotient. So you would assign a limit to h squared minus g over the limit of f of x in denominator, x goes to 4. Then you would separate the limits in the numerator, so you would have limit of h squared minus limit of g of x, this is h of x, divided by the limit x goes to 4 of f of x in denominator. All of these are go to 4. And then finally the square, right? So you can apply limit on h and then square everything. So when you employ the limit laws that we just wrote down, this is what we get. Now we have this block over here. This block is 2, right? It was defined to be 2. So you are replacing that block with 2. So we have 2 squared minus, I believe the block of g of x is -3, divided by 9. So this will be 4 plus 3 over 9, 7/9. So the limit of this particular combination of limits is 7/9, and you know each individual limit. We have no clue what the function f of x is, what g of x is. We just know what their limits are at 4, and we use the limit laws to separate these into individual limits and then eventually replace those limits with their associated values. So this can be, as you can see, this can be done without knowing the functions. Do we all understand the step where we are replacing? Because generally that's what the issue is when I look at exams. You're not understanding that all of this is -3. Even so, it's clearly defined as -3. So you are swapping out the entire expression with, right, with its value. The next order of business is to take a look at, say, limit x goes to 2 of x squared plus 3x minus 1. Observe the use of parentheses. If you don't write the parentheses there, then the limit would only apply to x squared, not to the rest of the problem. So these parentheses are not there for decoration, right? Because they look good. The parentheses are there because they are grouping the polynomial together to say that the limit applies to each term of that polynomial. If I am to write limit x goes to 2 of x squared plus 3x minus 1, limit does not apply to these two terms in that case. Notation is very important. Mathematics is its own language. You learn how to spell, right, and read this language. So parentheses group the polynomial, and the limit is applied to the entire polynomial, where on the example to the right, because there are no parentheses, limit is applied only on x squared. That could be a very cheap and evil and mean question on the exam. Because in the problem on the left, you will plug your 2 into both x's, On the problem on the right, you will only plug 2 in the first one, leaving the second one as x. So you have to be careful about those kind of things. I know it's picky, but this is what allows you to go and work in a country where you don't speak language, but you can operate 100% at your job because this is the universal language of the planet. Actually, I had a friend who worked for 4 years as a test engineer in Germany and barely spoke the language. But what he did was differential equations in engineering, which is all equations and notation like this, so he had no issues doing so. So what do we do? For a problem like this, we said, if you go back to the list of things to do, you always have graph and chart available. However, graphing can be tedious. Might not have graphing calculator. Chart is definitely tedious to compute values. So maybe we resort to algebra first as something that we can solve the quickest. And the first way and the simplest way to try and solve a problem is to plug value in. If that works, we are done. Well, in this case, plugging 2 in works, so we're done. 2 squared is 4, plus 6 minus 1. The answer is 9, and we walk away. So solving polynomial limits is cheap and easy because you will be able to plug in every time. But then we come up with a little bit spicier version of this, which is the rational function, which is a division of 2 polynomials. And this is where the limit and algebra collide big time for the first time. So say you have limit as x squared plus 5x plus 6 divided by, and let's say, well, x squared minus 2x or plus 2x, plus 2x. And x goes to negative 2. If you try to plug in negative 2, we get 0 over 0. And that is useless now, because 0 over 0 is not a finite value. Now you might want to say that the answer is undefined and move on, which also should be wrong. Let's see. So what is the thing that I could do here? Anyone?
You start with quotient rule or do that later?
Well, if we try quotient rule, then there will be 2 separate limits, and if we do 2 separate limits, each one will produce 0, so the answer would still be 0 over 0. So quotient rule and limit laws, unfortunately, do not work here. What is the only thing algebraically that I could work yet? No, it's the other F word. Factor, exactly. So, limit x goes to negative 2, we will factor both of these polynomials. So in the numerator, we'll have x plus 3, x plus 2. And in the denominator, we'll have x plus 2. You see how these two die? Right? Well, mathematical term is annihilate. That's what we actually use as the appropriate word. And the problem now is simpler. And also observe that if you now try to plug in negative 2, it works. So now when you plug in negative 2, you get 1 over negative 2, so answer is negative half. This is why you can't make claims about the problem if you get 0 over 0. When would you say that 0 over 0 gives you negative half as the answer? I can come up with another example that looks similar to this, that will give you 3/4, that will give you 5/8, that will give you any other value. I can fix these numbers here so that when they factor and you plug in whatever limit you got, right? So when you get 0 over 0, when you get infinity over infinity, you cannot answer does not exist, because clearly that would be the wrong answer. In some amount of problems, you will get lucky and that would be the right answer. But most of the time, no, it will not be correct. So your job is to carefully factor and cancel and then plug in and see what happens. So factoring is one of the techniques that it's used to solve the problem. Well, that's an evil example. Let's take a look at some of the examples. All right, so how about this? It's problem 32. It says limit age goes to 0. 3 divided by the square root of 16 plus 3h, and then plus 4 outside of the square root. What do you think? Answer, anyone? Yes, so just say it.
3/8.
3/8. So this is one of the simple examples, because if you try plugging in 0 for age, we don't get any weird things happening. It's just 3/8 and you're done, right? So as we plug 0 here, it kills the 3. Square root of 16 is 4. 3 over 4 plus 4 is 3/8. So this is the one that we just get to plug in and we're done because it worked, right? We didn't get situation like here where we couldn't get it to work. Yes?
Is there ever a problem where you can get like a number that's like a good number, but if you go through the laws, you get a different number?
No, never.
Okay.
It's math. So never. No exceptions to that rule. No matter which method you employ, and this goes across the field of mathematics for any discipline, any part of it, multiple ways will always produce the same answer. If multiple ways are available to us, we can try 10 different ways to solve the problem. The answer will always be 3/8 for this particular problem, and that is it. No exceptions to the rule. No deer and deers and sheep and sheeps and new and news. Exceptions in the English language and any other language or anything like that. We always have some kind of thing. Science and mathematics, because again science is based in on mathematics, no exceptions. That's it. So once you get the answer, that's the answer for all eternity. Cool. Well, I guess you're going to love this one. 41. Limit as x goes to 4 of x squared minus 16 divided by 4 minus x. This is the part where you talk to people who sit close and check your answer and make sure that you know their name, because I'm about to go around and check on that. If anyone wants the free haircut, just let me know. I'm amazing with that stuff. You're probably gonna end up looking like me or better. So yeah. So I've seen all the stuff they do, like this a little bit, and then not an issue. Free. Free. And the answer is -8. Did you bet your money on it? Good. So we factor the numerator, and then we also factor the denominator. So as you can see, I factored out -1 to make 4 minus x, x minus 4. These annihilate each other. What we get is, as we plug in 4, we get 4 plus 4 over -1, which is -8. Bueno. Let's see. Spicier version. Limit x goes to 9. Ready? Square root of x minus 3 divided by x minus 9.
Square root is just for x, right?
Yes. And the answer is 6. 1 divided by 6. 1/6. Anyone else? Got the same thing. Nice. I'm sorry? Oh, magic. Yeah. I actually seen them over there, the bones and things and the words and chanting and everything. It was. So what magic did you employ? Conjugate? Meaning that you multiplied to get rid of the square root. So method of rationalizing was used apparently, which is the square root of x plus 3 divided by square root of x plus 3. All right, let's see what we get. Square root of x times square root of x is x, and then minus 3 root x, and then plus 3 root x, and then minus 9, divided by, I'm not going to multiply in denominator, we're just going to leave it as is. When you take a look in the numerator, it simplifies to just x minus 9, right? So we have limit as x goes to 9, we have x minus 9 and then x minus 9 in denominator with a square root of x plus 3. So these cancel, and then we get 1 over 6. Anyone has sunglasses I can borrow for a second? Anyone? No. Oh, thank you. I promise to return them in one piece. Unaltered. Thank you. You have the bow to go with this? You have the bow to go with this? No. Remember what you said? All right. Now you're wondering what's going to happen. Nothing's going to happen. Just let's see. Same problem. Limit x goes to 9 of square root of x minus 3 over x minus 9. Same example. Ready? Limit x goes to 9, x minus 3 divided by, and now I'm going to factor the denominator. What I get is square root of x minus 3 square root of x plus 3. It's the boss move, all right? Yeah, you can factor anything. Anything can be factored. You write down x minus 5, it factors as a square root of x minus square root of 5, square root of x plus square root of 5. Now when you cancel, you get the same solution without going crazy. All right, so now cancel, and in one step we are at 1 over 6. Perfect. How about 46? Limit h goes to 0 of 1 over 5 plus h minus 1 over 5, everything divided by h. This is terrible the way I wrote this problem, so I'll just fix it. This line is not straight. The limit needs to be in line with line. All right, so what should we do? How do we approach this problem? Anyone? Yes? That's the answer, right? Okay, so what kind of witchcraft do you perform to get there? All right, consult your sorcery books. Anyone? What do we do? Yes?
I don't know what I did. I don't know what I did.
You don't know what you did. You did math.
I did math, but I don't know the step. I got one.
You got one? One what? Oh. Okay. Oh, I don't know. Well, I haven't done the problem yet. I'm asking you, what should I do? I'm stuck. I'm looking at this. That's the one. When you're looking at this problem, the only thing you can do is work on two fractions in the numerator and combine them. That means common denominator. What is the common denominator? 5 times 5 plus h. So the one on the left needs to be multiplied by 5. The one on the right needs to be multiplied by 5 plus h. Great. So this becomes common denominator of 5 times 5 plus h. In the numerator we have 5 minus 5 minus h. When you distribute -1, right, it becomes -h. These guys die. And now you have double fraction. So two that are far apart multiply in the numerator, which leaves you with -h. And two that are close by multiply into the denominator. And then this h dies. So you are left with the limit h goes to 0 of -1 over 5 plus h. And that is h is 0, -1 over 25. So the sorcery we employ here was the common denominator. Get the common denominator, work out the numerator, deal with the double fraction. So now looking back at all the examples that we did, what do you think, which one is the most important out of all of these examples when we started calculating from here, the polynomial? Which one would be the most important for our Calculus 1 concepts and future development? The last one. The last one is your definition for the derivative, actually. And these kind of calculations are coming up in 3.1. Actually, your 3.1 is nothing but this calculation. Over and over and over and over and over and over again. Right, that's it. This is 3.1. Practice problems like this. If your homework online, for whatever reason, does not include them, it should, look them up in study plan. So seek out exercises like this. Right now, we just say, take the limit. In 3.1, this problem will be stated as take the derivative or find the slope of the tangent line. And it's the same calculation. Identical. Nothing changed except the wording. Statement of the problem changes. Everything stays exactly the same. So that's 46. There is one more concept, I believe, which would end this. Yes. So one more concept here, and that is called the squeeze theorem, and 2.3 is done. So the squeeze theorem. So the squeeze theorem states that if you have a very nasty limit to compute and you're able to find two other functions that would squeeze the nasty function in between, sandwich it, and those two functions have the same limit at the point, the squeezed function, the bad one, will have the same limit. Think of a sandwich, right? So you have here, you have two pieces of bread, right? And you have a cheese. If you're allergic to cheese, put 2 slices. And you make a sandwich, right? So technically what you did is you squeezed a cheese or ham or whatever between those two. Now, think of the location of the sandwich. Whatever you take the bread, whatever is inside squeezed will go with it. You're not grabbing the cheese and moving it. You grab the bread and you move the sandwich, the cheese that it's sandwiched in between moves with it. Which is why if you think about a location of a sandwich, you can just think of the sandwich. You don't have to think about individual components. Your textbook, right, squeezes all of the pages in between, so you don't get to bring each page individually. You just grab the hardcover, right, for the book, and the whole book goes. So for this squeeze theorem, the sandwich theorem, is whatever the sandwiching functions do that badly behaved function that it's sandwiched in will do the same thing. So we'll write the formal theorem, obviously, first, and then we'll do a few examples to make sure. So assume this situation. So f of x is smaller than g of x is smaller than h of x. So g of x is the one that it's sandwiched between f of x and h of. This actually is called the sandwich theorem as well in literature. So it's either squeeze theorem or sandwich theorem, depending on the author. For all values of x near a, except no coughing, possibly at a. If limit x goes to a of f of x is equal to the limit as x goes to a of h of x, and let's say some number L, then, then the limit of the sandwiched function g of x is also going to be L. Now let's take a look at example of this, 2 examples or something. They provide very few examples. So say you are interested in the limit of x squared sine 1 over x as x goes to 0. You can't factor, you can't rationalize. None of the algebraic techniques we employed so far works, and definitely plug in doesn't work because 1 over x will give you infinity, and then sine of the infinity. What's sine of infinity? Right? The sine oscillates. So sine of infinity actually does not exist to compute. So you get 0 times does not exist. It cannot be computed by plugging values in. Can't factor, can't rationalize, right? None of those things work. But then there is this very important piece from your trig class, which is the fact that the range of sine and cosine functions is 1, which you can write as sine of x is less than 1. This is also for cosine, the same thing. And it means that all of the output values of sine and cosine functions are between -1 and 1. So this will allow, we can actually write a more advanced version of this now, because it really doesn't matter what kind of function you have within sine. The fact is that once you apply sine, the answers that come out of there are between -1 and 1. If you need graphical representation of this, your sine function is the wave that does this forever and ever. And as you can see, right, it's bounded by -1 on the bottom and +1 on the top. So that's what what range means, right? We talked about it last week. The range is the set of all possible y outputs, and you can't get anything other than numbers between -1 and 1. So now that we know that fact, what I can do is I can start from the fact that this sine 1 over x, sorry, that's the wrong arrow, there we go. The sine 1 over x is sandwiched between a -1 and 1. Okay, that's where I start. And then I look at the comparison, and I look and compare the function that I have and the function that I need. We observe, right, that I have sine 1 over x, but I need x squared times sine 1 over x. So the logical conclusion there would be to multiply through by x squared. And as soon as I do that, we have -x squared less equal than x squared sine 1 over x less equal than x squared. So what we found is that our function that we're interested in is sandwiched in between -x squared and x squared. Now those two are easy for limits, right? So now you take the limit of the n functions. If that works out to be the same value, the sandwiched function has to have that value. So I am going to look at the limit of -x squared as x goes to 0 and get 0. I'm going to look at the limit of x squared as x goes to 0 and get another 0. And now, by theorem, I conclude that the limit of x squared sine 1 over x, which was squeezed in between, is also 0. Because 0 is that L, that answer that we were getting on both ends, and whatever is squeezed in between has to have the same value. I will just switch quickly to the textbook to show you the graph of this. and why it works graphically. So observe your x squared, observe your negative x squared, and actually the function that you see in between is the x squared times sine 1 over x. You see how quickly it oscillates. It oscillates infinitely at that point there, and goes on and on and on. So we see that the limit of the red line is 0, limit of the blue line is 0, which means that whatever is squeezed in between must be 0 as well, because limits compute y values, and all of these y values collapse at the same point, which is 0, so which is the reason why the original function, right, the one in black here, is the one that has 0 as the answer. Trying to find more examples for this. All right, so find the limit as x goes to 0 of sine x over x given 1 minus x squared over 6 less equal than sine x over x less equal than 1. So,
Real quick, what page are we roughly on in the textbook?
I can tell you exactly. Or I can. Oh, I can.
You lied to.
77.
Thank you.
So what is the limit of 1 minus x squared over 6 as x goes to 0? It's 1. And what is the limit of 1 as x goes to 0? What is it? 1? Why? Why is it 1? Yeah, what is the limit as x goes to 3 of 1? How about 100? Yeah. Guys, when function is equal to 1, that's just a horizontal line. No matter which x you pick to approach, the y value is always 1. So there you go. So now we know that the end functions have the limit going to 1. Which means that by squeeze theorem, the function that is squeezed in between also has limit of 1. So, by the theorem, limit sine x over x is also 1. X going to 0. Yes.
If you don't get the same answer,
Then theorem doesn't apply.
it doesn't mean that there is no limit for that.
No. That means that this theorem doesn't apply. You have to use something else. Yeah. Yeah. So this one over here, see this how this statement says that the left function and the right function, right, the bread functions have to give the same number because there is equal sign in between. And then that same number is the answer to the one that it's sandwiched in between. And that's a very good question. If you don't get the same value here, then the if part of the theorem is ruined, which means that the rest of the theorem does not apply. Right? Perfect. That's the end of 2.3. Yes?
I'm sorry. Could you just clarify a little bit more why limit of 1 equals 1?
The limit is the y value of the function. Function y equals any number is always that number as the answer. Because when you look at, let's say y equals to 3, right? Y equals to 3 is the function that goes through 3. Any point that you pick along this line will always have 3 as the y value. So no matter which number you approach, from left and the right, the answer will always be 3. No matter where you are on the x-axis. The function is a constant function. It goes through 3, or it goes through 1, or it goes to 7. That will always be the answer. Another thing that I should mention, maybe I will see it later, is that if you have multiple variables, as you will see in chapter 3, you have x and age together in the problem. The limit operates on one, not on both. So if you have, let's say you have limit x plus 3age plus 8, and then x goes to 1. See, the limit operates on x, so you get to plug 1 there. We get 3age plus 9 as the answer. If you have the same question, x plus 3age plus 8, but the limit is now age goes to 1, the answer becomes x plus 11. So you have to be careful, right, to match the variable. The limit is the operator, which would operate on x because x is the one that approaches, and then all other variables that might show they're treated as constants, and you get to copy those. So those are some cool facts. And then maybe we can also write that the limit as x approaches any number of a constant c, the answer is always that c, which is the situation we just had with limit of 1. So limit of 10 will always be 10, limit of 100 is always 100, limit of negative pi over 2 is negative pi over 2, which we can capture with a single statement like that. Bueno? Yes, C. All right. Well, that's it for 2.3. Hope you're not disappointed. We'll take a short break and then 2.4. Ciao.